Hello and welcome to my talk about set similarity joins on multicores. This is the agenda. First, I would like to introduce the set similarity join and the filter and verification approach to compute it. Next, I would like to introduce our approach, experiments, and last but not least, answer some questions the reviewers had. What are the applications of set similarity joins? One application would be plagiarism detection. When you think about text which was copied from other sources, you could find these copied parts with this operation. Deduplication. When you think about a web search engine which only wants to produce one interesting result to the user, you could find similar ones which are not interesting with this operation. Fuzzy joins. When you think about information retrieval, where you want to join two tables based on the column names, which may be similar, you could use fuzzy joins for that, and the set similarity join is one version of a fuzzy join. So the input of a set similarity join is a set of records R, a similarity function sim, and a similarity threshold T. We want to get all pairs of records where the similarity is above this user-chosen threshold T. Let's have a look at an example. These are two records here, R and S. R has 5 tokens. In this case, they are words, but they could also be other data. S has 6 tokens, and they share 3 common tokens, as you can see here, which are marked in blue, or in the diagram in the intersection. One common similarity measure is the Jacob similarity, which is defined by the size of the intersection divided by the size of the union. In this case, it would be 3/8. So if this number would be above our threshold, we would consider these two records being similar. The naive approach to compute the set similarity join would be the cross product. Of course, this is usually not feasible, so this is why the filter and verification approach emerged. It uses filters to filter out hopeless pairs, which means that we get candidate pairs, which the number of candidate pairs is hopefully smaller than the size of the cross product. This is followed by a verification step. So each candidate pair is verified, so the similarity is actually computed, and if it's above the user-chosen threshold, it's in the output. The most important filter to mention is the prefix filter. So let's have a look at an example. These are two records here, and we can compute the prefix for these records with regard to the similarity measure, which is Jakar here, with the size of the records and the threshold, which is 0.5 in this case. So the prefix for R would be 5, and we can see this up there, which is underlined. And the prefix for S would be 4. And we can see already that they share one common token in both prefixes. And this is already the necessary precondition that these two records are similar. They have to share at least one common token in their prefixes. Otherwise, we can safely ignore this pair because it cannot be similar. Another important concept for the filter and verification framework is the use of inverted indexes. So here we have an example of an index with respect to these two records here. So we have tokens which reference or have a list of references to their respective records. We can now build this inverted index over the prefixes, and we can also probe it only using the prefix tokens. There are single core algorithms which compute the set similarity join using this framework. And there's an experimental study from VLDB 2016 which compares 7 of them. The authors say that this framework is maxed out, so they do not expect a big impact of further more sophisticated filters. There's also a study about distributed parallel set similarity joins, which are all based on Hadoop. And there's another VLDB paper from 2018, which compares 10 of them. The most important result, in my opinion, is that there is no advantage over single core algorithms, especially not regarding the handling of bigger data sets. There's also a line of research in the direction of GPUs. So single core underutilizes modern hardware, obviously. We have multi-core hardware today, and distributed parallel approaches potentially waste RAM and caching on multi-core systems. So when you think about the use of inverted indexes, which could be actually shared between executors, this cannot be done with Hadoop. So what's missing here is to have a look at multi-cores for this problem. How can this be used to speed up the existing approaches, and how do the filters behave? This is how typical modern hardware could look like. So we have multiple processors with multiple cores each, with caches which are sometimes shared, sometimes exclusive for cores, with different sizes, different access speeds. The processors are interconnected. Some processors have faster access to certain areas of the main memory. So the hardware is very complex today. How can we exploit this hardware for the set similarity join? So one approach would be the data parallel approach. When we look at our input data here to the left, we could partition it into disjoint blocks, and each thread takes one block and runs the whole set similarity join on this block by filtering and verification. Another approach would be the pipelined approach. So each thread is only responsible for one part of the work, which could be, for example, one filter, a second filter, and the verification. In order to do this, we need queues between the threads, and we need synchronization. And this turned out to be not very runtime efficient. So we did not follow this path of parallelization. We stick with the data parallel version. Design considerations. So we use the prefix filter and the length filter from all pairs by default for all our experiments. And we also use a somewhat comparable filter to MP join, which is to ignore entries in the inverted indexes which cannot match by length. We use the position filter from PP join and made this a knob, so we can switch it on and off and see how it behaves. As an implementation optimization, we use record inlining. So when you think about the input records with differing lengths, the standard way to implement this in C++ would be, for example, an array of a structure with pointers to another array which contains the actual tokens. Another way to implement this would be to also save the tokens in the record array. This is not trivial because the token lengths vary with each record. However, we expected that this saves some pointer chasing the CPU has to do with the standard way to implement this. We also made thread affinity a knob here, so we can actually pin threads to certain cores. Usually the operating system migrates threads between cores deliberately, and we thought it might be a good idea to pin this down to not migrate. And we also vary the block size to find the best block size for the runtime. This is the experimental setup. We use 10 real-world and 2 artificial data sets. The data sets are the same data sets which were already used in the 2 VLDB papers I cited before. You can see they have very different characteristics, so they vary in the number of records, in the record length, in the token universe, and in the size in bytes. The hardware we use has 2 sockets and 12 cores in total, and the DRAM size is 32 gigabytes. So as you can see here in the right column of the table, these data sets easily fit into main memory, also including all our structures like inverted index and everything else. First insight. The speed up we get on our machine is 2 to 10 times amongst all of our experiments. And this is a typical scalability graph we get. So on the y-axis, we see the speed up, and on the x-axis, we see the number of threads. The different colors mark the different thresholds we chose, which was thresholds between 0.6 and 0.9. From 0 to 12 threads, we get a nearly linear speed up. And from 12 to 24, it's not linear anymore, but still an increasing speed up. And above 24, we usually get a speed up which is not better anymore, even worse than the one from 24. So our machine has 12 cores. So up to 12 threads, we get a nearly linear speed up. And at 24 threads, we are at the number of hardware-provided hyperthreads. So this is usually the optimal runtime. So this is a very interesting result because hyperthreading is beneficial in our use case here. This is a counterexample. So for this data set, the speed up is limited to 2. Independent of the number of threads. And we found this is due to the short postings lists in the inverted index. We also repeated these experiments with enlarged data sets, and on the enlarged version of this Spotify data set here, the speed up was actually better than in this case here. Insight 2 is about the position filter. This is a typical graph we get. On the y-axis, we again see the speed up, and on the x-axis, we see the 3 different thresholds we chose. So we get, for 0.6, we get a speed up of roughly 50, for 0.75, roughly 25, and for 0.9, it's closer to 0. This is not a surprising result because for higher thresholds, we get less candidates and the position filter is less effective. However, what is interesting is that the position filter is beneficial for most data sets and thresholds 0.6 and 0.75. Compared to the results from the VLDB paper 2016, it is more efficient, so it's generally advisable to use the partition filter in the multicore case. We get 20 to 50% speed up for these 2 thresholds on all our data sets. Again, Spotify is an exception because it has only very few candidates, so the position filter is generally not good for this data set. How about our implementation optimizations? Record inlining and thread affinity are rarely good. So we can conclude that it's better to use the straightforward way to implement it and to leave, for example, the thread placement to the operating system. The batch size only has a very minimal impact between 0.7 and 1% in the best and worst case. So we did not really go into the details because we thought it's not very interesting. These were some questions the reviewers had. Why did you only use Jacquard? This is a very narrow topic. Well, the filter and verification framework can be used with any set similarity measure, like for example, dice or cosine. So it's not limited to Jaccard. We simply used it because to follow the research which has been previously done. Test the scalability with respect to dataset size. We did that. So we artificially increased all our datasets 5 and 10 times, and we also reported on the results in the paper. However, this problem is quadratic. So of course, when the input dataset size becomes too large, parallelization does not help against the quadratic nature of that problem. What are the differences between multicore and GPU-based approaches? There are two GPU-based approaches we are aware of, and both of them also use the filter and verification framework. One of them uses the CPU for filtering and the GPU for the verification, and the other one uses both. Uses the GPU for both filtering and verification. Why did you repeat each experiment 3 times? We did that to even out times we get, for example, from events we cannot influence, like I/O from the network or the operating system writing out logs, things like that. So we used the mean of the runtime of 3 times. Why did you choose thresholds between 0.6 and 0.9? If you would have a real-world use case, we could answer that better, but this is basic research, so we only can argue that for our data sets, a threshold below 0.6 gives so many results that would probably not be interesting to the user anymore, and a threshold above 0.9 doesn't give any results anymore usually, so it might also not be very useful to the user. Why did you use all pairs? Is it the best solution? No, it's not, but it's the basic algorithm which is used for all the other filter and verification based algorithms. So this is why we also used it as the basis and implemented filters from other algorithms, especially PP join on top. Details about the implementation, which threads did you use, OpenMP or pthreads? We used standard threads, which is a lightweight wrapper for pthreads in the Linux case. We used this because we wanted to use the pin threading. Otherwise, OpenMP would be sufficient to simply implement the blocking technique. How did the workload balance across threads? It balanced really well. So we think the blocking technique is suitable in order to balance the workload. Compare the runtime with state-of-the-art MapReduce on one node. So I think the intention here is to run a state-of-the-art MapReduce set similarity join and run a couple of executors on one node. Well, first of all, the study from 2018 suggests that this will not be very efficient because of the data replication. And second, I think it's hard to make this comparison fair because on one hand, we use C++ with sharing the inverted index amongst several threads, and on the other hand, we have a full-blown Hadoop framework in Java, which cannot share data between the executors. So I think it's hard to make this really comparable. What are the pros and cons of the proposed multi-threaded solution? I think the biggest pro is that it is very simple. The blocking technique is very easy, but the con would be we still have the issue of unfavorable data characteristics or too large data sets, which can actually break the filter and verification approach. What are the conclusions? So we get speedups between 2 to 10 times in our case. The position filter is more effective than in the single-threaded case, and hardware optimization, or the hardware optimizes execution already very well. One interesting direction of future work would be to integrate this with GPU. And another one would be to look at bigger data sets. For that, it would be necessary to reduce or get rid of the data dependency of the inverted index, and for example, to go into distributed execution again with a cost-based optimizer. So thank you for listening to this talk. If you have any questions, you can also go into the live session of the conference. And if you cannot do that or have further questions, you can contact me under this email address. And if you want to have a look at the code, you can do so in this Git here.